Hi, I'm Pat Hindle with Microwave Journal's Signal Integrity Journal. Welcome to this Signal Integrity, Power Integrity EDICON Educational Day session. Our EDICON online platinum sponsors this year are Samtec, ComSol, and Keysight, and our track sponsor today is Cadence. Please note that you can download the presentation slides for reference in the handouts window, along with some other handouts there from our sponsors. And note the session's being recorded, so it'll be available to watch later on and recommended to colleagues who weren't able to join us today. This session is the intersection of signal integrity and electromagnetic compatibility, given by Jay Diepenbrock of SIRF Consultants. Now I will turn the session over to Jay.
Hello and welcome to this session of EDICON Online, which I've titled The Intersection of Signal Integrity and Electromagnetic Compatibility. Here's my bio. I've worked in the industry for a number of years in a number of different areas, and I'm currently a signal integrity consultant with SIRF Consultants LLC. Here's the outline of what I'd like to discuss with you today. First, introduction. Next, signal integrity parameters and topics, EMC topics, and the conclusion. By way of background, the signal integrity and EMC communities have historically been somewhat separate, although in recent years the IEEE EMC Society made the decision to incorporate signal integrity and power integrity topics into their scope of view because there was no IEEE society that dealt with those two areas. Traditionally, the signal integrity community has worked primarily in the time domain, so dealing with things like oscilloscopes and pattern generators and TDRs, or time domain reflectometers, where the EMC community has primarily been working in the frequency domain using things like signal generators and spectrum analyzers, and to some extent vector network analyzers. The objectives of each discipline have been somewhat different. The signal integrity community is interested in transmitting signals from one place to another with minimum distortion and maximum signal-to-noise ratio, where the EMC community has been primarily interested in preventing transmission of signals, which could potentially interfere with the system itself or with other systems around it. But there is some overlap between the two disciplines, and I'll illustrate some of those today. Signal integrity parameters and topics have included signal transmission and reflection, eye-opening, insertion and return loss, skew, rise and fall times, and crosstalk. EMC topics have included harmonic content of signals, radiated and induced energy, common mode energy, resonances, plane splits, shielding, and grounding. We'll deal with a number of these parameters and topics today. Impedance is a fundamental property of a transmission line, which is determined by its geometry and the materials properties from which it's constructed. I illustrate in the upper right two transmission line segments, or two different impedances. The first one is the impedance of the line. The second one could be an impedance of a second line, which may be different from the first, or it could be something as simple as a terminating resistor. But mismatches between those impedances can cause reflections. The amplitude of those reflections are defined by the reflection coefficient gamma, which is defined as the reflected voltage divided by the incident voltage. This can also be expressed as the difference between the load impedance and the line impedance divided by the sum of the load impedance and the line impedance. Consequences of impedance discontinuities include signal reflections, false switching receivers, and resonances and radiated energy. Here's a simulated TDR of a network with two transmission lines and a terminating resistor. The voltage source to the left is a fast rise time pulse edge source, followed by a source resistance of 50 ohms, and that's connected to this transmission line network consisting of two lines and the terminator. In the first case, where Both lines are 50 ohm impedance, and the terminator is also 50 ohms. We see when the rising edge arrives at the beginning of the transmission line network, the impedance goes from 0 to 50 ohms, and then it stays at 50 ohms because the terminator looks like an infinitely long line of 50 ohms. In the second case, we change the second line, line 2, from 50 ohms to 100 ohms. And in the lower right plot, you'll see now the impedance goes from 0 to 50 ohms when the edge reaches the transmission line, and then jumps up to 100 ohms when it hits the second line of 100 ohm impedance. Then it drops back down to 50 ohms again due to the 50 ohm terminating resistance. Here's the third case where we have again two 50 ohm lines and a 100 ohm terminator this time. So the terminator doesn't match the line impedance. The impedance as plotted on the TDR starts out at 0, goes to 50 ohms when it hits the first line, and then jumps up to 100 ohms because it reaches the 100 ohm terminator. What's different in this case is if you look at the voltage on the line at node P1, the beginning of the transmission line segments, it starts at half a volt and then sometime later jumps up to a higher voltage. And this is due to the energy that's been reflected back from the 100 ohm terminating resistor towards the source. So it doesn't stay at half a volt, it jumps up to a higher value. Now if the source impedance was something different from the line, it would reflect off of that and go down the line again. So you can end up with some very interesting scenarios of reflections. But again, as I stated earlier, mismatches in impedance cause reflections. This is another illustration of that. Insertion and return loss are frequency domain parameters that describe, in the first case, the amount of signal loss as a function of frequency. And some of the causes of this are impedance discontinuities and frequency-dependent losses due to losses in the conductors, which could be skin effect loss, or could be dielectric loss in the board material or cable insulation. You'll see this is the differential insertion loss that's plotted here. It starts out at 0 at 0 frequency and then increases to a larger negative dB value as the frequency increases. Return loss, on the other hand, is the amount of reflected signal as a function of frequency. So for reference, the insertion loss curve is plotted here in red again, and the return loss, SDD11, is the return loss, which is, as you can see, has a number of ripples in it, but it starts out at a low value and then increases as frequency increases. The consequences of insertion and return loss are reduced signal to noise ratio and increased error rate and jitter. Skew is primarily looked at in the time domain, and it's the difference in arrival time of a waveform on one line relative to another. There are a couple of different types of skew. One is the skew between multiple single-ended signals, so the difference in arrival between one signal and another signal on another line. It could also be differential pair skew, where the difference in arrival time of the two legs of the pair is referred to typically as in-pair or intra-pair skew. Or it could be the difference in arrival time of a signal on one pair to the arrival time of a signal on another pair. That's referred to as pair-to-pair or inter-pair skew. The plots here illustrate the principles we've just discussed. Signals A and B arrive at the same time, so those two single-ended signals have no skew. But between signal B and signal C, which arrives later, there is some finite amount of skew between those two. On the right-hand plots, we see signals A and B, which are the two legs of a differential signal. The differential voltage is signal A minus signal B. The common mode voltage is the sum of A plus B divided by 2. And in this case, since there's no skew, there is no common mode voltage. Signal C and D, on the other hand, there is some skew between them, signal D arriving later. The differential signal shows a plateau region in the interim between the two signals' arrival, so it's at some intermediate voltage. The common mode voltage is the sum of signal C plus D divided by 2, and in this case, because there's skew between signal C and signal D, there is some common mode energy generated, which is undesirable. Some of the causes of skew are differences in the trace lengths or conductor lengths, or the geometry between the paths. You could also have differences in dielectric constant due to materials or due to what's referred to as the fiber weave effect. In printed circuit boards where you have regions that are consisted of glass fibers and other regions between the fibers where there's typically epoxy material or some other kind of insulating material. If the two legs of a differential pair are passing over different segments, so for instance one leg is over the glass epoxy, is over the glass weave, and the other leg is over the intermediate region or the epoxy region between the glass fibers, you can have significantly different dielectric constants in those two areas, and that can cause skew due to the difference in propagation delay caused by the difference in dielectric constant. This effect has been dealt with extensively at DesignCon and also in some papers in the Signal Integrity Journal. Rise and fall times are also of interest, and although we can't simulate a true pure square wave, the left-hand side, the first set of plots on the left tries to approximate that. You'll see the DC component at 0 frequency, and the fundamental or first harmonic is shown around 30 or so normalized frequency. This is for the equal rise and fall time case. The second case, we have equal rise and fall time, but they're longer than the rise and fall time in the first case, and you'll see that the second harmonic, which looks like it's around 60 or 70 in normalized frequency, is higher than it was in the first case, and the third harmonic is actually lower. In the third set of plots, you'll see that the rise and fall time are unequal, the rise time being longer than the fall time, and the third harmonic is significantly higher than it was in the second case. So change in the rise and fall time does change the harmonic content, and even harmonics are an indicator of mismatched rise and fall times, and also increase the amount of radiated energy. Here's a further illustration of the rise and fall time mismatch. This is plotting the common mode voltage on a differential pair due to rise and fall time mismatch. In this case, the rise time is 50 picoseconds and the fall time is 100 picoseconds. So you can see that the common mode energy is somewhere around 80 millivolts or something like that, maybe 90 millivolts. And then when we go to rise and fall time of rise time of 50 picoseconds and a fall time of 150 picoseconds, you can see now the amplitude of the common mode voltage is about 120 millivolts, so significantly higher than the first case. In this third case, we have a rise time of 50 picoseconds and a fall time of 200 picoseconds, so significantly slower. And the common mode voltage amplitude here is 150 millivolts, so it's now 15% of our desired signal of a 1 volt amplitude. So this is a significant proportion and can cause significant amount of radiation. In the early days of high-speed interfaces, there wasn't any control of the rise and fall time of the drivers used on the ICs, and often problems were caused because of the rise time mismatch and the generated common mode energy. Cable shields and grounding are also a topic of interest. Improperly shielded and terminated cable shields can cause both SI and EMC problems. So again, here's an area where the interests of the two communities overlap. Poor termination of signals can cause impedance discontinuities and radiation loops, which can cause radiated energy. Termination of the signal pairs to signal ground as opposed to chassis ground can also cause radiated energy on the shield of the cable. And so it's much better to terminate those cable shields to chassis ground rather than signal ground. The first picture shows a poor shield termination where the shield is stripped way back off of the signal leads, and so therefore the signal leads are basically unshielded for the last portion of their connection to the connector. The second picture shows what's referred to as a pigtail termination, where the ground wire is long and loose, if you will, inside this connector. We don't know if these two connectors were used metal back shells over them or not. The third picture does show a good termination, which not only terminates the shield to the metal back shell, but the metal back shell is connected to chassis ground. And of course, the metal back shell cover has been removed in this case, so that it's visible. But poor termination can cause a lot of problems. You might think of the pigtail case as a illustration of what happens when you use an oscilloscope probe with a long ground lead. They both create a big loop which can cause radiated energy and distort the measurements. Another interesting topic of interest is the return path, sometimes referred to as a ground plane or a ground path. In the first case, this is a printed circuit board trace that runs over an embedded ground plane or a buried layer, and the second gold shape there shows the return path for the current. So it mirrors the signal trace on the top layer. It really wants to follow that trace back to its source. In the case of a plane split, where there's a split in the ground plane under the signal travels across the ground split, you will see an impedance discontinuity where the signal travels over that split. But also, the return path is no longer straight. It has to come back and then go around that plane split, which does a couple of things. First of all, it makes the path a lot longer. But secondly, it also creates a loop area that can cause radiation of that energy out into space outside the board. So this can be a real problem. And it's analogous to the loop that we had in the previous slide looking at the cable termination. So the conclusion I'd like you to leave with is that the EMC and SI worlds are not so different after all. There's a lot of overlap between them, and as time goes on and speeds increase, there is more and more overlap and common interest between the two signal integrity and the EMC communities. It's sometimes a matter of perspective and even terminology as to what's being discussed. So there's a lot of overlap and common ground, and yes, I do intend that pun. Ground being a misnomer in a lot of cases. But the two communities and also the power integrity community that we really didn't discuss here today can learn from each other and help each other solve problems. So we've gone through some introductory remarks. We've talked about signal integrity parameters and topics, talked about EMC topics, and then the conclusion. If you have questions, please send them to me at surfconsultants@gmail.com, and I'll attempt to address them as best I can. But again, thank you for attending today, and I hope you've learned something and it's been useful to you.
Thank you very much, Jay, for that great presentation. So we now have some time for questions. If you have a question, enter it into the Q&A box, and we'll get to as many as we can. So Jay, first question, How would one use a spectrum analyzer for signal integrity evaluation of a system? I think you just need to unmute there. There you go. Jay, you there?
Pat, the audio is garbled. I can't understand it.
Okay, let me read the question again. So how would you use a spectrum analyzer for signal integrity evaluation of a system? Okay, I think we might have lost Jay there, so I'll collect questions and we'll follow up via email as he described. So this session has been recorded, so it'll be available later on to watch after the day is over, along with the other events at edicononline.com. If any of your colleagues would find it informative, please let them know. We thank everybody for joining us for this session, but stay tuned for our next one, how to fully verify SerDes-based designs before prototype and manufacture. Thanks for joining us today.